Hey everyone, I'm Anish and welcome back to PrepFusion. So today we'll be starting the lecture 4 of root locus diagram, right? So in the previous lectures, we understood the steps required to plot the case 1 of root locus where my k is greater than 0, right? Where I have negative feedback and k is greater than 0, right? These two conditions you have to keep in mind. Obviously, when we will go to other cases, there we will understand what is the difference between this case and the other case, right? So now like in this lecture I have skipped a few steps, right? One of the step was basically angle of departure and angle of arrival, right? So that I will cover in this one with example, and also I will cover few more examples, and like this one these two I will solve slowly. After this what I'll do is solve fast, right? So because in exam, right, obviously you have to solve fast, not slow, but as you are just understanding right now, so you solve it slow with all the steps, find out all the values, right? But in exam you don't find out all the values. You can use intuition as well to understand how my root locus diagram will look like without calculating the exact diagram. Okay, so yeah, let's start with this question. So we have to plot the root locus diagram of the following OLTF, right? Of the following OLTF, where my g of s equals to k divided by s plus 1, s plus 2, s plus 3 into s plus 4. So what was the step 1? Step 1 was to identify my open loop poles and zeros, right? So what are my open loop poles and zeros here, right? I don't have any open loop zeros, right? Open loop zeros I don't have any, but I have open loop poles. How many I do have? I have 4, right? So -1, -2, -3 and -4. So I have 4 open loop poles, as you can see from here, right? Directly it is just in factor format, so very easy to see, right? When does it blow up to 0 or when does this thing blow up to infinity? So I have, so number of poles, how many do I have? So p here, right? P equals to 4, or you can write it as n also, no, like m also, so it doesn't matter. Okay, but number of zeros, how many I have 0, right? I don't have any zeros. So how many branches I will have? Number of branches is equal to 4 minus 0, which is equals to 4 itself, right? I will have 4 branches. So from here we can understand, so I will have 4 roots always. For one value of k I will have 4 roots. But what is the problem here? I have 0 zeros and 4 poles. So how many number of virtual poles, virtual zeros or asymptotes I will have? I will have 4, right? Because like as you can see from here, only at k equals to infinity it should terminate to zeros, but I don't have any 0 to terminate, right? So I will have to make 4 virtual zeros. This all we know. So let me plot the sigma s plane basically and note down the roots, right? This is sigma and this is j omega, and this is -1, -2. I should make this a little bit bigger actually, so that would be easier, and I will keep this one, so I can't do that. Fine. So this one is here and this one is here, let's say, and this one is here and this one is here. Okay, so I have, like, this is -3 here also, and this is -4. Okay, so I have 4 roots basically. So I will have 4 branches, right? 4 branches. So number of virtual zeros, I can write number of virtual zeros I will have 4, right? 4 virtual zeros I will have. Okay, so yeah, this is the basically step 1. What is the next step? Next step is to identify my location of my closed loop poles on the real axis, right? So step 2, identify closed loop poles on the real axis. So I will not write those because that will just waste time. So from here, right, if I just, okay, I need to reduce the size because this has become giant actually. So yeah, let's reduce the size of this one. Okay, and what can I see from here, right? What can I see? So what was the rule basically that you used to follow? It was the angle rule, but it has been refined to what? That, so that on the right hand side of my test point, right, I should have odd number of zeros or poles, addition of those things, right? So here what do I have? I have one pole, right? always at until this point I have always one pole. So yeah, this range is lying within the real axis, right? This range is valid. Okay, and if I check this range, right, if I start from here, what do I see on the right hand side? I have two poles, right? Two poles. So hence this range won't be valid until here, right? Because until here I have always two poles on the right hand side, right? Right hand side of my location, basically right hand side of my test point. So here I have always two poles. So this location again is not valid. But if I see from here, right, if I see from here, I have three poles, right? I have three poles. So this location will be valid. This location will be valid. Okay, so here what are my valid ranges on the real axis? So my valid ranges are S basically belongs to -1 through -2 and minus, it is actually union, so it is, we can give it like union, right, and -3 to -4. Okay, so S belongs to this range basically. Okay, this will lie in the root locus. Okay, will lie in the root locus. This will lie in the root locus, right? So if this lies in the root locus, that is done. Okay, we know the ranges, right? Now what do we know? Obviously the roots will terminate like originate from here and then they will break away. So I will have two breakaway points. Like from intuition you can understand, I am just going step by step, but directly from here you can solve this question, right? How this roots will break away and this will go on like this. But you might have the doubt that can they go on like this? Okay, if they go on like this, then this has to also go on like this. Okay, so yeah, there is an issue. So what will happen is this will go on like this one and this will go on like this one. Okay, but how do you understand this will happen? Because they have to cross over here, right? They have to cross over here. So all that we will understand, and let's solve this question, then we'll understand it. So what was the next step? Next step was to find the asymptote, right? Angle of asymptotes. So anyways you can understand that there will be 4 asymptotes, but what will be the angle of those things? So what was my step 3? Basically finding theta asymptote. So theta asymptote, okay, what was the formula for it? It was 180 divided by P minus Z into 2K plus 1, where K belongs to 0, 1 and P minus Z minus 1. Okay, P minus Z minus 1. Okay, so this is what my theta asymptote is, right? So yeah, let's put the values of K. So how many I have? Basically this, right? This is 4 minus 1, which is 3. So 0, 1, 2, 3, right? 4 asymptotes. So like how many will I have? I will have like this. You can write as plus minus only, but we'll only take the plus. Okay, we'll only take the plus. So first one will be basically 180 by 4, and next one will be 180 by 4 into 2. Okay, not 2, sorry, 3, and like this it will go on, right? Like this it will go on. So this is 45 basically, and this is 135, right? And this is how much? This is 5 times this 45, which is 225, and this is how much? This is 7 times this 45, right? What is 7 times 45? 280, and add another add another 35, so it is 315. So basically we're adding in steps of 90. That also you can see, right? We're adding in steps of 90. Okay, so from there also you can calculate, like it is easier to calculate only. So yeah, this we have found out, but in the previous examples, right, we haven't found out the centroid, right? Centroid of asymptote. What does the centroid of asymptote mean? Basically the common point of all the asymptotes on the real axis is known as the centroid. Once we draw the root locus, there you will understand it better, right? But what was the formula? Okay, obviously I haven't derived it yet. Okay, and I think I will skip the derivation because it is not that important. Okay, and it will not come in very handy. Okay, so I have skipped the derivation, right? So here, right, the formula for the centroid is real parts of poles of g of s, that is the OLTF, minus the, like, this is summation, minus the summation of real parts of zeros of OLTF, right, divided by p minus z. So number of poles minus number of zeros. Okay, so yeah, how do we write it? Basically it is a summation of the real parts of the poles of g of s. Okay, so what are the real parts here, right? I only have real poles, right, real open loop poles. Basically it is summation of the real open loop poles. Okay, real parts of the open loop poles, and this is the summation of the real parts of the open loop zeros. By real part, what do I mean? If I have complex poles, right, complex poles, what will happen? What will happen even if you don't write this real part, right? It doesn't matter, because let's say I have complex poles, right? I have complex poles of -1 plus j and -1 minus j. So they will always come in complex conjugate format. Now if I add these two up, what do I get? I will get the real component, right? So that is what this is telling. Okay, that is what this is telling. Okay, but even though if this real wasn't there, right, real part wasn't there, only summation of poles of g of s, h of s, then also my statement would have been valid, because I would have always got complex conjugate poles. Okay, let's say let's name this. I would have always got like this -2 and -3. Let's say I have 4 poles, right, and if I sum this one up, if I sum this one with the complex values intact, right, if I sum this one up, what do I get? -1 -1 -2 -4 -7. Okay, I get -7. Okay, now let's only sum the real parts of this one. So if I sum the real parts of this one, what do you get? -1 -1 and -2 and -3. Again I get 7. Again I get -7. So that is what I was explaining you, that it doesn't matter if it's real part or not, because like we are getting complex conjugate poles, so this part is getting cancelled anyways. But like just to be like more formal, so they write this one. Okay, so I will delete this one. So what is our centroid here, right? What is our centroid here? So we have to add the real parts of poles of g of s, h of s. So like what are the poles? Basically this, right? -1 -2 -3 -4. So -1 -2 -3 -4, these are my poles. Okay, now what are my open loop zeros? What are my open loop zeros? I don't have any zeros. If I don't have any zeros, what will I do? I will just subtract a 0 for it. Okay, I don't have any zero. I could have subtracted nothing also, but just to represent you, I subtracted a 0. Okay, so if you don't have any poles, you write instead of poles 0. Okay, so this means I have no zeros. This means I have no zeros, right? Now the denominator, it is number of poles minus number of zeros, which is basically equals to what do you say, 4 minus 0, right? 4 minus 0. Okay, so this comes out to be like 7 3 10 10 by 4, which is -2.5. so my centroid of the asymptote will lie on the -2.5. now what does that mean? Let's see. Okay, basically I haven't like let me copy this one and draw the like asymptotes where are they present and draw the centroid of them, right? Okay, so I see that my asymptote, right, what are the angles? Angle one is 45, one is 135, one is 225, one is 315. so if it is 45, right, if it is 45, so like what I can say is my centroid is here, right? My centroid is here, right, between these two. So we'll mark my centroid. Okay, now with respect to the real axis, I am 45 degrees at angle, right? So with respect to this real axis, I have to go plus 45. That means I have to go anti-clockwise in the 45 degree angle, right? So anti-clockwise 45 degrees angle. So here it will be 45 degrees angle, right? So this is the first asymptote, basically first virtual zero, right? Okay, now what is the second? Second is this one. The second is this one. Okay, it is basically, if you measure it correctly, it will be 135 degrees, right? Basically it moved like 135 degrees in the anti-clockwise with respect to the x-axis, or you can say 90 degrees from here, right? So this is not exactly accurate, but just to try to understand. Okay, so not that accurate drawing I have. So again I will move again another 90 degrees in the anti-clockwise direction, basically in the plus 90 degree, right? Because the next asymptote is 90 degrees like behind this one, right? So Okay, so this is again 90 degrees behind this one, and the last one will be 90 degrees again behind this one, or minus 45 degrees also you can say, because if you subtract, right, if you subtract minus 360 from here, what do you get? You get minus 45, right? So yeah, you can say like that also. Okay, so yeah, this is basically my location of asymptote and my centroid. So I hope you understand the centroid, right? Centroid is where all the asymptotes meet in the real axis. Okay, although you can see this is not a straight line, this is a rough diagram, that's why. But here, right, where all the asymptotes meet, right, this is 2.5 and this is the centroid. Okay, and these are my like ranges of real axis where my location of closed loop poles will lie, right? So yeah, I hope you got it. So now let's go to the step 4. What is the step 4? I have to find the break in and breakaway points, right? So are there, just logically tell me, are there any break in points here? Are there any? There aren't, right? Why? Because there are no zeros itself, right? There are no open loop zeros, there are only open loop poles. So what is the possibility? There will be breakaway points, and from this diagram itself I can understand there will be 2 breakaway points, because I have 2 adjacent poles here and 2 adjacent poles here. So this one will come over here and they will break away, and this one will come over here and then they will break away like this, right? Like this they will break away, and this one will break away like this. Okay, so yeah, this is how my root locus will be, right? So from here, right, break in point not possible. Why? Because no zeros present, no zeros present. Okay, so now let's obviously now we will calculate the breakaway points. Okay, there will be 2, so I have to reject few solutions also. Let's see what do I have to reject. Okay, so like what I am going to do is do a very tricky thing, and that you may be upset, so I will obviously not calculate it fully. I have already written it down, so yeah, I will just calculate it slowly, then like a bit of it, then I will rightly write the solution, because that will just waste our time, because third order, right, solving third order equation is not easy, right? So that's why. So this is my g of s into h of s, right? This is my g of s into h of s. Now at the end, right, at the end, what is my a of s? A of s is 1 only, right? A of s is 1. Okay, and what is my b of s? B of s is this one, right? B of s is this one. So now what you do is basically the differentiation of this one will be 0 only. So what we will get? I will get b dash of s into a of s should be equal to 0. Okay, so okay, am I doing this right? Yeah, b dash of s into a of s should be equal to 0, right? Should be equal to 0. Now because like I will explain it further. So like a dash of s into b dash of s, b of s minus this b dash of s into a of s will be equal to 0 for calculation of break-in point basically. So now I know that my a dash of s, right, a dash of s will be 0. Okay, my a dash of s will be 0. So if my a dash of s is 0, then what does that mean? That means this is gone, right? This is gone. I have only left with this one. So from here what I can write is my b dash of into a dash of s equals to 0 itself. Okay, so you solve this one. Okay, then okay, this is the homework for you, and you can use the help of like any online calculator also. Okay, for finding the roots of cubic equation. You solve this equation, then what you see is you get 3 solutions, right? Okay, so I've written it down here. Okay, so obviously I don't want to waste you guys time, so I will get 3 solutions: s b1, s b2, s b3. Okay, I will get 3 solutions. So if I get 3 solutions, one will be okay minus 1.35. okay, another one will be minus 1. okay, is it okay, another one will be minus 2.5 itself, and another one will be minus 3.618. okay, so another one will be minus 3.618. and for this, right, I've also calculated the value k, that I will tell later. So from, just tell me which ones will lie on the root locus and which ones will not lie on the root locus. Can you say it from here? So we know the range, right? We know the range. What is the range of my s? So I'll copy that range here. This was the range, right? where my root locus will lie on the real axis, right? So from here, what you can refer, right? What you can understand. Okay, so it should lie between -1 and -2 here, right? This point is between -1 and -2, so this is a valid point. This is a valid point, right? Okay, now this point, right, it isn't lying between this one also and isn't lying between this one also, so this is an invalid point. So this is an invalid point, so I'll cross this one. Okay, and what about this one, right? So this is lying between this one, so this is also a valid point. So I will have two breakaway points, right? And these are the breakaway points basically. Okay, these are the breakaway points. Now what are the values of k for these breakaway points? I have, like, if there is any calculation error, you just tell me, right, in Telegram. So I found it out to be almost equals to k approximately equals to 1. K approximately equals to 1. So yeah, these are the values for my breakaway points and the value of k, right? So k, as I can see, is coming positive, so hence these are valid. If you calculate the value of k for this one, it will come out to be negative, right? So yeah, basically I found out everything right now. And what about the angle of, like, step 5? Again, I will have to skip this one. Next example we'll do what about the angle of arrival and angle of departure, right? So here, right, I don't have any complex conjugate poles or zeros, right? I don't have any complex conjugate poles or zeros, hence the concept of angle of arrival and angle of departure will be, we have to skip, because I don't have that complex poles or zero. In the next example we'll understand what is the angle of arrival and what is the angle of departure. So step 5, skip. But before that, obviously what I can write is the breakaway and breaking points from where they are breaking away. Okay, so if I copy this one and reduce the size of this one a bit, okay, so if I reduce the size this one a bit, what do I see? I see this will break away from somewhere around here, right? Somewhere around here, right? And somewhere around here, right? Okay, someone like this, and it will go until this asymptote, right? Go follow this asymptote basically, right? So yeah, this was it. Now let's understand. So here, right, they will cross somewhere, so we have to find the last step is the crossover point. So what do you do in the crossover point step? Simply put s equals to j omega, right? Simply put s equals to j omega and find the crossover points. So what is my equation? Where did it go? Okay, here, this is my equation, right? So, like, yeah, this you have to solve it. Will be time consuming. So what you do is, like, this will be s square plus 3s plus 2 s square plus 7s plus 12 plus k equals to 0. So what do I get? So again I have to multiply, right? So this is multiplying, this is difficult. So this becomes, I will multiply s square first, s to the power 4 plus 7s cube plus 12s square plus 3s cube. What you can do is, like, what I will suggest you to is, you can directly put s equals to j omega here, right? So that will also make your calculations a bit easier, just by computing the real and imaginary terms. So if I put, okay, let's see if I am right or not. No, like, no, you do it like that one only, right? So yeah, that one only it will take the same time, so just thought now. So yeah, this is 3s cube. Okay, 3s cube, I was here. Now this is 21 s square and this is 36s. Right? Now this is 2s square (14s) plus 24 plus k equals to 0. Now let me like, make the like terms together. So this will be s to the power 4 only, then this is 7s cube plus 3s cube, so this is 10s cube. Now this is 12s square and 21s square. And do you have any square other terms? No. So this is 12 and 21. So this is 33s cube, right? 33. Okay, am I doing this wrong? Okay, I have 2 square here also. So 12, 33, 35 plus 35s square. Then what do you have? I have 36s and 14s, which is basically 50s, basically 50s, and I have 24 plus k, right? 24 plus k. So what do we need to do? Simply put s equals to j omega. So okay, so if I put s equals to j omega, I will just equate the real and imaginary terms. So this will be like j to the power 4. What is j to the power 4? It is 1. Okay, I will not explain further. So this will be omega. Okay, this you do it by yourself. Like, what is j cube? So this will be minus j omega cube. Okay, because j cube is minus j, right? And plus j square is minus 1. So I will write minus 35 omega square. Okay, and this I can write as plus 50 g omega plus 24 plus k, right? Plus 24 plus k. Okay, so this I can write. So now right now, like what else do I need to write? So I need to equate the real and imaginary part. So what I will do is, first I will equate the imaginary parts, because I have only 2 terms here. So that's why I will equate the imaginary. That is looking easier to me. Equate the imaginary parts to 0. Basically on the right hand side, what is the imaginary component? It is 0, right? Here it is 0. 0 plus j 0. So I can write minus 10 j omega cube plus 50 j omega equals to 0, right? So like omega equals to 0 is not a solution. Omega equals to 0 is not a solution. Why? Because we know we will have 2 crossover points, right? That we got from here. Okay, we'll have 2 crossover points that we already know. Okay, so omega equals to 0 is not a solution. Even if you put omega equals to 0, right, you will get k something negative. If you put omega 0, you will get k minus 24, which is again not possible, right? So yeah, omega equals 0 is not a solution. So what is the solution? So I will cancel omega from, like, I will divide by omega on both sides. So I will have omega square equals to 5. Okay, so omega square will be equals to 5. So omega equals to plus minus under root 5. Okay, so this is my frequency of oscillation, or you can say my crossover points. So crossover points, right? S crossover equals to plus minus j under root 5, as s equals to j omega, right? S equals to j omega. So now let's equate the imaginary parts. So 2 equals to 0. So like, sorry, a real parts equals to 0, which is 1 plus g of s into h of s equals to 0. Okay, here I could have also written the same thing. Okay, just to like make you understand a bit better. Okay, so yeah, so this is this case. Now, like, what are the real things? It is omega to the power 4. Then I have minus 35 omega square, then I have 24 plus 24k, right? 24 plus k equals to 0. Okay, so yeah, this one is this one. Now I put the value of omega to under root 5, right? So this will be under root 5 to the power 4 5 omega square plus 24 plus k equals to 0. So what is my k equals to? So like this is like 35 into 5 minus 1, this is like 5 times 5 minus 25, right, minus 24. So what is 35 times 5 is basically 150 and 175, and again I am subtracting by 25, so it becomes 150 only. So 150 minus 24, which is equals to 126. Okay, so this is my value of k crossover, right, k cross. Okay, so I got my k value right from here. Okay, so yeah, or what you could have done is use the Routh-Hurwitz table also. How? So yeah, that will take time, but still, okay, let's use it. But this is the easier method. Okay, don't need to stress much. These you follow. Okay, just to show you that you can use that method also, just to have the revision of Routh also, right? So you should have all this in revision, right? You should not forget the previous chapter that we just did, right? So you should keep this in your mind. So yeah, let's now pause this video and solve this equation, right, using the Routh-Hurwitz criteria, right, RH table basically. So how to solve this using the RH table? So let me first write the table here, right? So this will be s to the power 4 s cube s to the power 0, right, s to the power 0. And this will be 1, this will be 35, and this will be 24 plus k, right, 24 plus k. And in the bottom, what do I have? I have 10, 50, and this is 0. Okay, so yeah, this is 0. Now what will happen? Let's compute, right? Let's compute. So this one will be 10 times 35 minus 50. So 350 minus 50 is 300 divided by 10 itself. So this is 30, right? Let me write this in different color. 30. Now what is this? So again, right, this one will come over here because I have a 0 over here. No need to think much. So 24 plus k, right, 24 plus k. Now again I have to compute this one. So this is basically a bit difficult to compute. So okay, I will write this in small letters. This will be 1500 minus 240 minus 10k divided by 30 itself. Okay, and what will be this one? This I have 0 over here, right? I have 0 over here, so this one will be simply a 0. Okay, simply a 0. So what I will do is I will shift this columns in this side, so to accommodate this one. So yeah, this one will be 0 only. And what will be this row? So this row, right, will directly come over here, right, because I have a 0 over here. So this row I can write in different color. 24 plus k due to this one, right, to this one. Okay, so yeah, now what happens for my what do you say, system to be marginally stable, right? So I need to have like a row of 0 here, right, row of 0 here. I will remember, right, row, I need to have a row of 0 to get imaginary roots or like symmetric roots basically. Okay, so I will equate this equation equals to 0. Okay, then I will get my condition, right? Else what would have happened? If it was greater than 0, my system would have been always positive, stable. If it is less than 0, my system would be always unstable, because after this point, right, what does the crossover points mean? After this point they are going into the right half plane, so system becomes unstable. So from until this point my system is stable because all four poles lie on the left hand side, right? So once they cross over, right, once they cross over, they become unstable. Okay, so yeah, this is what basically happens, right? That's why if I equate this one with 0, that is the critical point about which my system goes from stable to unstable, right? So equate this one with 0. So -1500 minus 240 minus 10k divided by 30 equals to 0. So what do I get? So basically, right, if I divide by 10 everything, right, so this will be 150 minus 24 equals to k, and k cross, right, k cross. From here also I can calculate that it will be 126. Okay, so from here also you can understand, right, like you can understand that like k is, if it is greater than minus 24, it is stable, right? If it is greater than minus 24, it is stable, and between this 126. Okay, so but minus 24 key value is not possible. What we will choose is, like, you have to equate this one greater than 0. All the first columns of my Routh-Hurwitz table, right, should be greater than 0, positive basically. Not all the first, sorry, all the like the first column of my RS table should be greater than 0. So I can't write minus 24 because minus 24 is not a valid value for k. K can be more than 0, that is fine, but k has to be less than 126. Until that, k is stable, right? Sorry, my system is stable. Now what is happening at 126? My system becomes like marginally stable, you can say, because there are complex conjugate poles. So now there are imaginary poles on the geometric axis. But what is happening after this? So it becomes unstable. So it becomes unstable basically. So yeah, this is what is happening now. Like let's I have drawn the root locus diagram, okay, and all the values, all those things. So here, like as you can see, the crossover points, I've written it down, the values of k I have written down, right? After this point it is going unstable, right? And until this point all these are stable, right? And here I've like done the asymptotes and the break-by points, you can see, right, minus 1.35 and 3.16, and this is the centroid, right, centroid. Okay, so yeah, this is the basic plot. I don't want to go into too much details. Okay, you can pause the video and like zoom in and stuff for this one. Okay, and here is the like the MATLAB plot, right? So I have done the MATLAB plot also to like see you, like you can do it by yourself also, whichever you are in doubt, right? You can do it in MATLAB also and check, right? It is coming exactly like this. Okay, it is crossing over here, and these are my points, and yeah, similar. So just to give you like a basic practical knowledge, we use this in MATLAB also, right? So yeah, this was it for this question. Okay, now let's go for the next question. So again, pause the video and try to solve it for yourself, right? So you have to plot the root locus of the following OLTF. Okay, plot the root locus of the following OLTF, and yeah, check my answers, right? So here that extra concept will be used, which is of the concept of angle of asymptotes and angle of angle of arrival and angle of departure. Why? Because if you compute the open loop poles and zeros, you see that my open loop poles are on the are complex conjugates, right? My open loop poles are complex conjugates. So yeah, let's start. So again, right, I will do the step 1. So what is the step 1? Step 1 is identify the open loop poles and zeros. So what is my open loop poles? So open loop poles I have to find. So what I can do is basically, right, I will copy this one. This one is too long. So basically, right, I have to equate this one with 0. So basically this is minus b, which is plus 2 plus minus b square, which is 4 minus 4ac, which is 8 itself, right, divided by 2a. So which is, if I get this one correct, this is plus minus j. Okay, plus minus j basically. Okay, you do this, like you get minus 4 over here, and which is j under root 2, sorry, j2, my j2, and this 2 get cancelled, so I get 1 plus minus j. So I have complex conjugate poles. So I have complex conjugate poles, right? So if I have complex conjugate poles, these are complex conjugate open loop poles, sorry, not poles, just open loop. These are open loop poles. Now let's calculate the open loop zeros. Basically, let's calculate the open loop zeros. So open loop 0 is only 1. Okay, so it's basically -3, right? Okay, so what are the number of poles? Number of poles is 2 and number of zeros is 1. So number of branches, what is my number of branches? So number of branches equals to what do you say, 2 itself, right? Because the number of poles will be decided the number of branches, so it is 2. But I have only 2 zeros, so at k equals to infinity I will have another asymptote. So whenever I have only one asymptote, where does it go? It goes to the -180 degree, right? So number of asymptotes equals to 1 itself. So if it's 1, so like it is the number of virtual zeros basically. Okay, it's equals to I can write z virtual, right? Z star, or you can say, right? So these are my all the information about the first step, right? I got to the first step. Okay, let me now locate the open loop zeros and poles. So I have two complex conjugate open loop zeros, right? Basically this is what plus j and minus j, right? And these are two complex conjugate poles, and one open loop zero I have at the s equals to -3, right? -3. Okay, this is plus, sorry, this is plus. So what will happen is this will lie on the right hand side. So this will start off being unstable, right? So what I'll do, I'll shift this axis on this side. Okay, sorry for like I messed this one up at starting. So this will be minus. Okay, I have to cut this one up. Okay, and this sigma, right? This sigma. So yeah, this is this one. So now, right now, what you need to do is like plot the zero. So open loop zero is around here, right? It's in -3 basically. It's in -3, right? So open loop zero is on -3. So basically, right? What I can understand is from intuition, what you can say is obviously I can't lie around here, right? My test point won't lie around here. That is the step 2. So let's do the step 2 itself. Step 2 is basically finding the test like valid location of my closed loop poles on the real axis. So so this is this one. So like if I extend this one a bit, right? If I extend this one a bit, someone is actually calling me constantly. Okay, that's the issue. So I can't I will not stop this recording because this recording is going good, flow is good, so I won't stop this one. So yeah, what is the step 2? Finding the real axis points, right? So here, right, if my test point lies around here, how many right hand side poles I have? You can either say 0 or 2. Okay, you can say 2 or 0. So due to the angle contribution, the angle will be 0 itself. Due to 2 of this, right, angle contribution will be 0. So here, this range, my test point can't lie. Okay, even from that rule also you understand, right? Only even number of poles are lying here. So no, here how many number of poles and zeros are lying? Odd number, right? You can say 3. These two are getting cancelled due to the poles, but this 0 is contributing a -180 degrees. So hence I get a valid test point here. So what is my range of my closed loop poles in the real axis? It is basically S belongs to -3 and -infinity. Okay, so this is my valid range, right? Within this range I will get my test valid poles of the CL type, right, in the real axis. Now here, right, I know like there will be one asymptote, right? So that also we will do in the next step itself, finding the angle asymptote. That we already know it is 180 because that is now we have mugged that one up basically. Like, it's in our head, right? So step 3 is asymptote, right? Theta asymptote. So again, right, it is 180 divided by p minus z. So p minus z into 2k plus 1, and k is going from 0 1 p minus z minus 1. Okay, so only have 1, right? So it will be k equals 0 itself, so it will be equals to 180 itself, right? That we know. Now centroid sigma c won't be there because my whole asymptote is lying on the real axis itself. Okay, hence like it is always intersecting with the real axis. Okay, no concept of sigma c, no concept of centroid. Okay, my asymptote is lying on the real axis, so there is no concept of centroid at all, right? So yeah, so I got my asymptote. I will just copy this one and draw this one further. Okay, I'm going slow for these 2 examples, and from next one what's right, I will go very fast. Okay, okay, this is my asymptote basically. So yeah, now let's go for the step 4, that is a breakaway breaking points. Now tell me, will there be breakaway or breaking points, or will there exist any points? There will be, right? Because like here what I can see, I have like this is a virtual 0 itself, but I have 2 adjacent zeros, and like this point has to somewhere come from here, right? Okay, these two have to come here, right? And they have to break in, basically break into this real axis. Okay, so this will come here over here, and they will break into the real axis. So yeah, there will be what, breaking points and not breakaway points. There will be only one valid breaking point. So step 4 is basically breakaway point. No, right? No breakaway point, only breakaway in point will be there. So how to calculate the break-in point? Again, right, copy this equation. I will write this as, so what is my a of s from here? All right, you can do that one also, dk by ds equals to 0. That one also you can do, like whichever suits you. Like you can write 1 plus this equals to 0. Then what you do is make dk by ds equals to 0. From there also you can find it out, but like that does the same thing that I do, right? That, okay, not this, yeah, this is only, okay, yeah, this is fine. So like that is the same thing that I will do here, right? What I will do is basically, what is my a of s? A of s is s plus 3, and what is my b of s? B of s is s square minus 2s plus 2. Okay, so these are my a of s and b of s. So again, right, what is my a dash of s? A dash of s is 1 itself, and what is my b dash of s? B dash of s is 2s minus 2. Okay, so b dash of s is 2s minus 2. Now what we can do is just equate that equation. What is that equation? That equation is like a of s into b dash of s minus a dash of s into v of s at s equals to s. Break-in point will be equals to 0, right? So that is what that dk ds also does, right? That does the same thing. So what is a of s? A of s is s plus 3. Feeling sleepy, but I don't know why. My head is getting blasted. This is 2s minus 2. And what is a dash of s? A dash of s is 1, and b, what is b of s? B of s is s square minus 2s plus 2. So s square minus 2s plus 2. So that is my b of s equals to, right? So let's equate this equation basically. So this is 2s square, okay, and plus 6s minus 2s, so plus 4s, and this is minus 6, right? So this is what I get on the left hand side, and this is simply s square plus 2s minus 2. So the minus sign is going inside the bracket, right? So this is s square plus 6s, and this is minus 8, right? Minus 8, okay. So this is what I get. Now let's compute the break-in and breakaway points. So I've already computed this one down. So like what you get, the solution is minus 6 plus minus b square plus 4ac, okay. 4ac is 32 itself, right? So because this becomes plus because I have minus 8, right? Divided by 2a, then minus 6 plus minus 68 by 2. So if you solve this one, again I have written it one down, right? So like this under root 68 will be something like plus minus 4.12, right? 4.12, okay. So now I will get 2 points, okay. One will be something like minus 7.12, and another one will be something like plus 1.12, right? So which one is valid? So like from that location, right, where did it go, the range, okay, yeah, here. So my poles, closed loop poles on the real axis can only lie between minus 3 and minus infinity, right? Okay, in between that range. So in between this range, so this is lying in this range, but this isn't, right? So this will be valid one, and this will be invalid. This will be invalid, right? So yeah, for this value, right, for this value, the value of k will be come out to be something 16.12, something like that, okay. Or yeah, 16.24, okay. You just check the values, okay, and confirm it, right? So like this, okay, this is base b2 actually, sorry. Okay, so yeah, so basically, right, so this is my value of k. So I will not compute it, that is up to you, okay. I just written it down and I'm just writing the results, that will just waste your time. So for this one, if you calculate, you will get some negative value, okay. So yeah, from that also you can understand this is not a valid point on the root locus, okay. So let me copy this one, previous. Now I know the break in points also, okay. Now I know the break in points also. So what are my break in points? Basically they will come something like this, right? Now I don't know the angle, but some from somewhere, right, they will come something like this and break into this loop. One branch will go over here, another branch will go over here, right, and terminate to k equals to infinity. And what is this point? This point is minus 7.12 and k equals to 16.24, right? So this is my point, okay. But still, right, I don't know how will they start from here. Why? Let's come to that only. So this is the step 5, okay, absolutely the start of this step. So what is the like angle of departure we'll study first. So I should write here angle of departure. So angle of departure I will study first. So what is angle of departure? We have to locate the angle of departure at an open loop complex pole, right? So why is it called departure? We'll see. So let's first read this. The angle of departure at an open loop complex pole is equals to 180 degree minus the sum of angles made by vectors from other open loop poles to this pole plus sum of the angles made by the vectors from other open loop zeros to this pole. Basically nothing has come to your head, right? So yeah, what is this telling? So yeah, we'll obviously understand this. Just understand this. Why is this called departure? Departure it is called because, right, here, right, so obviously it has to leave, right, my branch has to leave, okay, so obviously it can't go to directly real axis, it has to leave, okay. Now what will be the angle by which it leaves with respect to my x-axis? Because the thing is, it can leave in any direction, okay. I can say it can leave in this direction, you can say it can leave in this direction, you can say it can leave in this direction, in this direction, in this direction, in this direction. So but there has to be only one direction, right? There has to be only one direction, okay. That will be a valid point, but how to identify that one, that obviously we'll do, okay. So that is the main concept of this angle of departure and arrival. In terms of this like real polar zero, what was happening is that I, like, for a single pole, right, where the multiplicity is 1, that is I don't have a repeated pole, my this branch, right, can only go in this real axis, it can't go in this axis. Why? If it goes in this axis, I will need another branch to go in this axis, okay. Then here, right, I will have two branches, but still I need another branch which will terminate to this virtual zero, okay. So but I only have two branches, I will have two branches, I already used my two branches here, then who will provide the branch here, okay. Hence that's why we eliminate that case that they can't go in the complex axis. But if I had a repeated pole here, then it would have been possible. It would have been possible that if I have two poles, then I would have gotten one extra branch, then this could have left in the complex plane. But now I don't have, I have only single pole. So if I place, like if I say that no, this one will go like this one, right, so then as the coefficient of my polynomial are real of my characteristics equation, hence something has to come over here also, right. But that is not possible because I will exhaust my number of branches, I have to give another branch here, right. So yeah, that's why we eliminate the case here. But why can't we eliminate the case here? Because if something is leaving from here, the other branch will leave from here, right. So it's not an issue, okay. If something is leaving from here, the other branch can leave from here, right. So it's not an issue. So I am not exhausting my branches, I am exhausting my branches here, right, because this is leaving from here. So I hope you get the point, okay. So I have tried to explain it to you as much as possible. So this is the concept of basically this angle of departure and arrival. So for open loop zeros, and I will again explain you, okay, in the next few slides again explain you, right. But what I was getting at is, why is it called angle of departure? Why not arrival? It is called departure because you are departing, right. Because from where does my root locus start? My root locus starts from my open loop zeros, so it is departing from here, okay. My root locus is departing from this open loop zero, that's why it is known as angle of departure. So leaves the pole, it leaves the pole, okay. So this is what my angle of departure is. Now this is the formula for angle of departure. I will try to give you a basic hint, right, but this is the basic formula for angle of departure, okay. So one thing you do is how to remember this. So first I will tell you the technique how to remember this, because at the end in the gate exam you will only use this, not use any concept or like obviously not use the derivation. Basically obviously you will use this, but obviously I will give you the basic intuition also how this came up. But how to remember this, whenever you're calculating the angle of departure, right, what is that for? It is for pole. So pole will get subtracted, basically summation of all the poles, okay. What does that mean? Basically if I want to calculate the angle of departure of this pole, right, I have to calculate the angle of this pole with respect to all the other poles, right. So if I see from this pole, I am seeing a plus 90, I'm seeing with respect to x-axis basically. So I have to calculate the angle of this pole with respect to all the other poles. What do I mean by that? So like if I have this pole here, right, and I have to calculate the angle of departure for this one, so I will calculate my angle of this pole with respect to this pole in the x-axis direction, okay. How much angle I have to move to get to this pole with respect to my x-axis. So what does that mean? How much angle I have to move with respect to my x-axis to get to this pole, for which I am calculating my angle of departure, okay. So for all the other poles, so what I will make a x-axis here, and if I see, right, I have to move 90 degrees. I will also give you like written things also to how to exactly calculate the angle of this all these things, theta p and theta z. I will give you that thing also. So I have to move plus 90 degrees. If I move plus 90 degrees, I can see that it is above me, right. So if you are in the straight head and if you move plus 90 degrees, you are seeing that that pole is lying above me, right? That pole is lying above me, exactly above me. So you're rotating your head exactly 90 degrees, right? Exactly 90 degrees. So yeah, that you got, right? That you got. Okay, so the angle due to this pole, okay, for me to reach to this pole, right, is plus 90 degrees as I'm rotating plus 90 degrees rotation. So that is basically my theta p. Okay, we'll do more examples from there also, you will understand. And what is my theta z? What is my theta z? My theta z is this one, the angle due to this open loop zeros, right? Angle due to this open loop zero. Now I'm lying around here, right? I'm lying around here and I have to reach to this pole, right? Reach to this pole. Okay, now how much head do I have to move? So I don't, this is not exactly lying above me, okay, this is lying just in front of me, but in some direction, so it will be something positive angle in some direction, okay, but obviously it won't be exactly 90, it will be between 0 to 90, okay. That will calculate, how to calculate that will explain it to you, okay, in the next few slides. So this is what my theta z and theta p is. Now whenever I need to find the angle of departure, what you remember is that always subtract this theta p, because I am calculating it for pole. So for pole always subtract theta p, okay. So this is the how to remember this one. So you have to understand how to remember the formula also, okay. So for pole, okay, for, or I can say for departure, as it is for pole, right? For departure, as it is for a pole, we know, so we have to subtract theta p, hence subtract theta p. I'm telling you how to remember this formula. This is not just like a concept or anything, this is how to remember this formula, because this will also help you in gate exam also. So subtract theta p, okay. So yeah, this is what my angle of departure is. I have a call, so I will just attend that call, and next we'll start with angle of arrival and explaining the concept of both of those, right? Sorry for the interruption. Yeah, sorry for the interruption actually. So yeah, we'll start with the angle of departure, basically angle of sorry, we done the angle of departure. Now we'll do the angle of arrival. So this is my angle of okay, something happened, nothing. Angle of arrival basically. So what is my angle of arrival? Now why is this called angle of arrival? Basically like the departure thing I have told, right? Now if I would have had two open loop zeros over here, then what would have happened? My root locus would have terminated in these zeros, right? They would have terminated, my root locus would have arrived at the zeros instead of leaving, right? Because at zeros they terminate. So as they are arriving, that's why they are known as angle of arrival, okay. At what angle they are arriving with respect to the x-axis, at what angle they are arriving with respect to the x-axis, right? So that's why as they're arriving, right, root locus is arriving at my open loop zero, right? So yeah, from there you can understand why is this called angle of arrival, right? Now this is the formula, okay, the same formula only, just how you remember, right? I will not explain, because explaining this is just, you will also not understand anything. Just written it down, you read it for yourself and try to understand. But what is the important point here is that for calculating of angle of arrival, what do you do? Okay, for arrival, basically to the open loop zero, what do? You subtract the zero, summation of the zero angle, okay. That's how you remember it. Subtract the theta z. So subtract summation of theta z. This is just a way to remember this formula, because sometimes you may forget this formula, right? So yeah, now let me give you again like the explanation that I told in that, right? So what I will do is I will take this example only, I'll take this one only, right? And what I will do is this one I will take, right? And yeah, this one I will take. So copy this one, paste this one over here. So as I was telling, right, that this, from this complex conjugate poles, my branch can leave in any direction, okay. But here they had only one path, this direction, right? Because if they had left here, then I would have had to choose another branch here. Now if another branch is here, right, then I have already taken two branches, but something has to terminate over here, right? Something has to come over here, okay? But like this has to come only from this real axis. I've already taken the two branches, but here also I should have some branch, right? If they are like this one also, here there should be some branch, but I've already exhausted my two branches, so I don't have any remaining branches to give to this pole, right? Okay, because for one value of k I will get two branches, so I already have got here two branches, but here also they have to terminate, right, in the virtual zero. I don't have any branches left, that's why. I will got the point. That's why this can only lie in the real axis, okay? From one branch is leaving from here, another branch will leave from here, and they will again like break in, right? Break in. We have already got clear that concept. So now, right now, what is happening to this? This can go in any direction. This can go in like this direction, this, okay? But what is the actual direction? How do you know that? So that for that, obviously the concept of angle of departure is present, right, for this pole, okay? This can go in this direction, this direction, this direction. Just what will happen? I'm only using one branch, because another branch won't directly come out from here. Another branch will come out from this pole, so that is fine, right? Because I need two branches, and two branches should terminate from the two different poles, and that is exactly satisfying the condition here. But here, right, I need two branches, and two branches should terminate to two different zeros, okay? Two different zeros. But here, right, they are not terminating, they are only terminating to one zero. If I choose complex conjugate zeros here, right, sorry, if I choose like complex conjugate root locus here, right, that's why. So here the condition is satisfying. I need two separate poles, and two separate poles are leaving from their respective location, right? So they can go in any direction, but obviously they will only go in one direction. Now what is the direction? So that direction will prove. So let me do it for zeros as well, and then we'll understand it also better, right? So like just to give you like more visualization for zeros, right? For zeros, let's say for example, if I have a pole over here and a zero over here, two zeros over here, what will happen? They will arrive, right? They will arrive at this. So if one of them arrives at this, one of the location of the closed loop pole is at this point, so another will be at this point. That is not an issue, because another one is arriving at this pole. So two different positions, like two different poles are arriving at two different open loop zeros. That is fine. That is satisfying my condition. But previously here it was not. If I would have left like two different poles are leaving from here, I already exhausted my two branches for this one pole itself, but I have to leave from here also, or like something has to leave from here, but I don't have any branches left. So this is not virtual zero, okay? This is just an example, so I can take an example like this is pole, okay? So just don't go, this is just an example, don't go into the specifics, right? So what can happen? So multiple, like it can come in from multiple directions, right? Come in from multiple directions. So but only, obviously it will have only one direction. Multiple solutions isn't possible. So how to find the angle? So let's find the angle, okay? So let's find the angle basically. So what we will do, how to find the angle? So I will give you a brief intuition of how to find the angle basically. So I will again paste this diagram, right? So what I will do, I will again take a test point very near about the pole in which I am interested in finding the angle of departure. So if I am interested in finding the angle of departure here, I will take a test point here, right? So if I take a test point here, what do I see? So let's say I am taking a test point ST over here, right? ST over here. Okay, if I take a test point ST over here, now what is my characteristics equation? Like these are my open loop poles and location 0, so I will not, I don't need to write my characteristic equation, okay? So that I already know, right? So my test point ST is here. Now what does this test point ST has to satisfy? Just remember, this is the basic condition. Through this only all the proofs come for root locus, right? What does this has to satisfy? This has to satisfy the magnitude condition and the angle condition. Now magnitude condition is for the value of k, and the angle condition is for the location of my test point. So I am in the location of my test point, so this ST has to satisfy the angle condition. So choose a test point ST very close to my desired pole, okay? choose a point ST very close to my desired pole. Okay, so yeah, that you can choose, right? That you can choose. Now what next? It has to, my ST has to satisfy my angle condition. So point ST has to satisfy my angle condition. Okay, point ST has to satisfy my angle condition. What does that mean? That means basically this G ST, H of ST should be equals to plus minus 180 degrees into 2k plus 1, right? Like any multiples, like k can be any odd, like k, this is odd, like odd multiples of 180 basically. Okay, so how to find this angle, right? How to find this angle? So how many vectors I have? I have this one pole, this one 0, and all, that's it, right? That's it. So what I will do, I have to find the angle like this one. This is one vector, right? Let's say this is theta p1, okay, for the pole 1, and this is, let's draw it with another color. This is this vector, right? This is, let's say, theta z, okay. Only I have 1 0, so I will write theta z only. So I have to find this angle. Now how to find this angle basically? So what you do is, like with respect to x-axis, right? So you can further extend this here also. What you can do is further extend this here also. So what is each of these angles contributing with respect to my x-axis, right? With respect to my x-axis, that is the theta z and theta p. So that is what it has to satisfy. Now what is the thing is? The thing is, I am at this test point, right? I'm at this test point, not at the pole itself. I'm at the test point. So the test point has to satisfy that 180 degree angle condition, right? I'm at the test point, and some value will come at this test point also, right? From the pole, right? So this is theta z, and okay, so this is actually got messed up a bit. So okay, what I will do is I will delete this one. Okay, delete this one because I've made one mistake, so sorry for that. So what I was trying to explain here is, I'm reaching this test point, right? Reaching this test, so I will draw this a bit thinner actually. So from my 0, I'm reaching this test point. Okay, reaching this test point. So what are the each poles are contributing and zeros are contributing overall to this test point will determine my basically condition that whether this test point will lie on the root locus or not, right? So this is, let's say this is theta p1 and this is theta z, right? And also some angle will come from here also, right? Let me take some angle will come from here also, from the theta. Okay, I will name this one theta p2. Sorry, I will name this one as theta p2 and this one as theta p1, right? So let's name this one as, okay, with respect to x-axis, so this will be something around like this one, theta p1, and theta, I will write this one as theta p2. Okay, so now what is the interesting part? I have 3 angles, right? So all of these 3 angles, if they are satisfying, what does that angle condition was? So how do I write my characteristics equation? So let me first write the characteristic equation. So okay, let me copy it. Where is it? Yeah, here, right? Copy this one. This I will delete. This is 1 plus g of s, and this is 1 plus this, right? This is 1 plus this, and this is 1 plus this. Now if we know all this, right? If we know all this, now what was the angle condition? Angle condition was basically, if I have a g test point, right, this should be equal to 0, and if I have a g test point, so that is equals to basically this sorry, what am I doing? So this k equals to minus s square minus, sorry, okay, if I find the angle of this whole equation, right? If I find the angle of the whole equation, what do I get? I get that my g test point should be equals to minus angle of this one should be equals to minus 180 degree, right? It should be equals to minus 180 degree. Now this is this angle basically. So if I calculate the angle of this one, what do I see? That sorry, like not this one. So this, okay, I should write this in a better manner, so else you will get confused. So my g of s equals to -1, so hence this becomes this, right? So my k of s plus 3, g of s is this one, right? G of s is this one, equals to this one, s square minus 2s plus 2, right? This is g of s. Now if I find the angle of this one, what does this mean? So if I find the angle of this one, angle of g of st is basically equals to, I have two, right? Here I have two poles, so I will get two poles here which will come in negative, because this is in the denominator and this is in the numerator, so this will be positive. So this will be plus theta z and minus two angles I will have, minus theta p1 and minus theta p2. So this is what the formula I will use, right? This is exactly what the formula I will use. So here, right, I have 1 0, okay, so I will add this angle due to this 0 and I will subtract the angles due to these poles. That I will do, okay. So so coming back to the question, basically, so basically what will be my angle? So, oh sorry, one thing also I should write is angle of k also. Angle of k is also in the numerator, but this is 0 basically, because it is a positive integer, okay, and it is a positive integer with respect to the positive axis, it is 0 itself, right? It is 0, so it is only 0, so we choose not to write it. So yeah, that is what we got, right? Now I should write here also, because during the negative, like when we will do the complementary root locus, right, that angle of k will be very, very important. So I will have angle of k also, okay, angle of k also. Now as k is positive, k is greater than 0, hence angle of k equals to 0, right? K is positive, so like I will explain with the basically graph also. So let's say my k, this is k, right, value of k, okay, and this is the positive x-axis basically. So if my k is lying around here, okay, with respect to x-axis, what is the angle? 0, right? 0. That's why. So I hope you got the intuition why it is 0. So yeah, that is that. Now what are these? Like this is theta z, theta p1, theta p2. So that is what I've written, right? Theta z, theta p1, theta p2. So that we got. Now what is the important point is, as my st point is really near to this pole, right, minus p1, really near to this pole, what I can write is, like, I will further derive this one, that as my st is really near to my p1, okay, p1 pole, right, minus p1 pole basically, then what I can deduce is that st I can write as almost equals to p1. st I can write as almost equals to p1. So let me first like write this better manner, then you will understand. So this will be 0 plus, okay, I can write it 0 itself, so I don't need to. So what is this theta z? Theta z is this st minus of minus z1, right? The angle between the st and the z1 vector. So this is the vector basically, right? And what is this theta p1? Theta p1 is st minus of minus p1, right? Pole location. P1 I'm assuming as like pole location, right? So I'm assuming the standard form, s plus p1, s plus p2, s plus p3. So s equals to minus p1 is one of the poles. So that's why I'm writing it like this one. So what is the next angle? It is st. So don't worry even if you don't understand this, right? This will not be hamper in your gate preparation, because no one tells you this. It's just, they will just directly tell you the formula, okay? So but this is just to give you a basic intuition. So don't worry if you are not understanding this, if you are not able to grasp this, not an issue. But if you are able to, this will only help you in preparation, like give you a better idea of the how did the concept came. So minus of minus p2, okay? So these are my angles. These are my angles of theta p1, theta p2, all those things, right? I hope you understand how to write angles. So now I will replace this st of p1 over here, like st p1 over here and here, right? Here I will not replace, because this is the angle that I want to find. This is the angle by which my test point leaves the pole. So as you can understand from here, right, if my st is really close to this pole, so if my st is just here, I can find that this is the angle by which my test point leaves the pole, okay, at just near this pole. So I want to find that angle itself. At which angle with respect to the x-axis this leaves, this theta p1 I want to find, right? Theta p1 I want to find really near to this pole. So I will not replace this st equals to minus p1 here, okay? That is how no use. But other places I will replace, okay? As this becomes really near to this pole, so the angle is with respect to this p1 itself. So this becomes with respect to this p1 itself, and this becomes with respect to this p1 itself, because this st point is really near, right? And this angle I want to find out. So okay, so I hope you got, right? As this point is really near this one, so this angle is with respect to my p1 itself, because this is really small distance, and this is also with respect to my p1 itself, right? So yeah, that is this one. So that's how we got this. So this I will replace with, basically this is the angle of departure, okay? So this is the angle of departure basically, and all the other things are simple normal things, okay? So what is this equals to satisfy my condition? This will be equals to 180 degrees, right? 180 degrees. This has to satisfy my angle condition. So what I can write, okay, I will write minus 180 because it's same, because that at that side it will go plus 180, so it doesn't matter. You write minus 180, 180, it's same, right? You go anti-clockwise 180 or clockwise 180, it doesn't matter. So this is my theta departure. So I can rewrite this equation, right? Theta departure equals to 180. I can write this one as summation of theta z. Now as I have only one 0, so only I can write 1 0, but this I can write as summation of theta z basically. So this one will be plus, like I put this theta departure to this side and this 180 to this end, right? That's only what I did, right? So okay, if you don't like, still I will write this on down if there is some confusion. This will still remain minus 180, okay? And this I will write as summation of theta z, okay? This I will write summation of theta z. As I have only one 0 here, it is only theta z, okay? But if I had multiple zeros, then all the zeros would have been added, okay? We'll do few examples and there you will understand, okay? Then minus, this is the theta angle of departure, right? Angle of departure. Then this is minus summation. If I had multiple poles, I would have added there theta p, right? I would have subtracted theta p, okay? So yeah, this is this one. So now I will take the theta departure to the left hand side, and this minus 180 to here, right? So this becomes plus 180 theta z, okay, and minus summation of theta p. So this is the thing that was written, right, at the first slide basically, okay? And we derived it, okay? Obviously the summation you won't understand because we only had one pole and one 0. If I had multiple poles and 0, then you would have understand. Now I found out a theta departure for p1, so I should write here as angle of departure for p1, right? Angle of departure for p1. So this is my angle of departure for p1. So if this is my angle of departure for p1, now what is my angle of departure for p2? Can you tell that? Can you tell me that? So basically, right, angle of departure for p2 will be just the negative of this one, just the negative of this one. Why? Because they are complex. From intuition, if you want to understand, as they are complex conjugate pole, for example, let's say my departure is like this one, right? So what is the angle of departure? It is, let's say it is 135 degrees with respect to the x-axis. Now here, right, this pole has to be complex conjugate, so it can't leave like this, okay? Because this location and this location are not complex conjugate. Which angle it can leave? It can leave like this only. If this is fixed, right, this has to be fixed. They are complex conjugate, so that's the beauty. So this will leave like this one. Now what is the angle of this one? How can I understand? The addition of these two angles, right, will be total 360 degrees, okay? Will be total 360 degrees. Why? If you do the derivation for this one, right, you will get to see that it is just the negative of this one, okay? Just the negative of this one. Or by intuition, what I can see, if it is leaving like this, okay, it is leaving like this 135 degrees, okay, then it has to leave like this one. This will be 135 degrees then, okay? Because from here it is 135 and here it will be 135, okay? So yeah, that's how you can understand. But this is minus 135. So what I can write is my theta departure p2 will be equals to simply 180 not 180, simply 360 minus, as the addition of those two will be theta 360. Or how can I further write it down? So I can further write it down as minus theta, because 360 adding 0 is same, coming back to the same rule, equals to theta departure P1 itself. Okay, so yeah, this is what we can say as complex poles will be mirror image about the x-axis, right? Okay, as my complex conjugate poles will be mirror image about the x-axis. So yeah, this was the concept about the angle of departure and angle of arrival. Similarly, I will not prove it for angle of arrival. Okay, the homework is for you prove it for angle of arrival. Okay, so yeah, you prove it for angle of arrival. Okay, so obviously this is not even asked in gate exam, but to give you intuition, I did for the angle of departure. Now the homework is you do it for same proof you apply it for angle of arrival, right? So now what are the key points about my angle of departure and angle of arrival? So just read this through. Angle of departure is only valid for open loop complex conjugate poles. Obviously, like from poles only it will leave, right? That's why angle of departure is only valid for that. Angle of departure gives us the information about the angle by which the closed loop pole will depart from its position. Basically, it gives us the information like the angle by which it will leave the closed loop pole. That you already know, right? So yeah, the angle of departure for the other complex conjugate open loop pole will just be the negative of previous one that we just established, right? If the magnitude of breakpoint is greater than the magnitude of centroid of the asymptote, then the angle of departure will be less than minus 90 plus 90. This is just information, okay, and this may help you in exam to solve a question faster. So I don't remember this, okay, but if you want to remember, these are just a few things to keep in mind, okay. But I don't remember this because I forget, I tend to forget things, so I just solve there directly only, because you never do, right? You may mess up a point, right? Switch these two. So yeah, just read these 2 points just to give you information who like to memorize stuff, so they can memorize this, okay? Else no need, right? No need. Now what is angle of arrival? Angle of arrival is only valid for open loop complex conjugate zeros, so they will only arrive at the zeros, right? Angle of arrival gives us the information about the angle by which the closed loop pole is arrives near the complex open loop zero. Basically, what is root locus? Root locus is the locus of my closed loop poles, right? So my closed loop poles, when it arrives near my open loop zero, at what angle with respect to the x-axis does it arrive? That is the information that my angle of arrival gives, and similarly the angle of departure also gives for that respective pole also, right? So yeah, have you got it? So yeah, now let's obviously come back to the real question. So we have to find the angle of departure in this case, right? Why? Because let me take this, what should I take? This one, right? I had 2 complex conjugate poles, open loop poles, so not the arrival, I have to calculate the angle of departure, right? So I had 2 complex conjugate poles, so like 2 branches will leave, right? 2 branches will depart from this 2 complex conjugate poles, but at what angle? That I have to find out. So let's find the theta departure. So let's understand how do we find the angle of departure, and same method will be established for angle of arrival also. We'll do multiple examples after this and we'll understand how to find angle of departure, how to find angle of arrival, all those things. So angle of departure for P1, right? Let's name this as P1 and let's name this as P2. How do we find that? So what was the formula? Let's try to memorize the formula. It is 180 minus theta, it will be plus because I am finding a pole, so for pole Z will be 0 will be plus and pole will be minus. So that's how you remember, right? Pole will be minus, okay, all the other poles, right? So what is theta Z? So if I see theta Z, right, so what is this x, okay, let me delete all this, right? These are not important. So what is this distance, x-axis distance with respect to the pole, right? What is this distance? This is my xz, which is equals to, this is minus 3 and this is what? This is +1, right? This is +1. I hope you remember, right? The location of my open loop poles were +1 plus minus j. Okay, so this is +1. So what is the distance? Distance is 4, right? Distance is 4. So x-axis distance is 4, and what is the y-axis distance? So y-axis distance with respect to my open loop pole is 1 only, right? This is lying on the the x-axis itself, and this is 1 unit above, right? Plus j means 1 unit above. So this is 1. Basically this is 1. Okay, so yz. Okay, so I will understand, right? So what is the case? My x and y both are positive. If my x and y both are positive, then what I can write my theta z as? What I can write my theta z as? So theta z I can write simply tan inverse y of z y of z upon x of z, right? This is what I can write my theta z as. So if this I can write my theta z as, then as both of them are positive, right? So what is this equal to? This is equal to tan inverse 1 by 4. So this is the angle that I am interested in, right? Theta z, and I will understand, right? This is simply, what is tan theta? Tan theta z, it is height upon base. So that is what exactly I am calculating with respect to the x-axis. Simply I am applying sine rule, right? But trigonometry, simple trigonometry I am applying. So I hope you understand it. So this is the height and this is the base, right? Okay, simply I am applying tan theta equals to height upon base, and then I am finding the angle of theta. So if you do it, okay, this tan inverse 1 by 4, it comes out to be, I have written it down, it comes out to be 14 degrees. Okay, almost approximately 14 degrees, right? Now the same case what I will do for pole. So I hope you are understanding, right? So what is going on here? I am moving my head above, right? I'm moving my head above, but only by 1 units, but I have to go 4 steps forward. So I have to go more forward than above, so that's why this angle is coming little bit less, right? Little bit less than 45 basically. If these two are equal, then this would have been 45 degrees only, right? So yeah, but here what is happening here, right? For this P2, what is happening? What is my x P2? Like x distance with respect to my P1. What is my x P2? X P2 is 0 itself, right? Because I don't have to move ahead or behind, right? It's simply above me, directly above me. So I don't have to move ahead or behind. So xp2 is 0. Okay, and what is this xp1? Sorry, what is the yp1? Yp1 is simply 2, right? Because I'm moving 1 unit and then again 1 unit, but this doesn't matter. Why? I will tell you, just explain you. So basically both of them are positive or equal to 0, both of them are positive. So again tan inverse y upon x, and tan inverse 2 upon 0 is basically tan inverse infinity, which comes out to be 90, right? Which comes out to be 90. Okay, so theta z, theta p2 basically, theta p2 will come out to be 90. Okay, theta p2 will come out to be 90. Now if theta p2 is 90, then what is happening? Then basically, right, what we can say is that it is 90, and always for the complex conjugate pairs of poles, right? If I want to calculate this angle of departure for this one with respect to this one, so what I will see, I have to move 90 degrees down, right? So it will be simply minus 90 this time, because this yp1 is plus 2, but there it will be in the negative direction. I'm below this, so it will be minus 90. Okay, so yeah, they will always be either 90 or plus minus 90. Okay, if they are complex conjugate to each other. So if I'm moving down, so I'm seeing down which quadrant it is lying, right? It is lying in the 4th quadrant. I hope you understand, right? With respect to this one, I'm moving down, right? So it's lying in the 4th quadrant. So always measure with respect to quadrant. So with respect to this one, which quadrant I'm lying? I'm lying in the 1st quadrant. The pole, where is the pole P1 lying? With respect to this 0. With respect to this pole, where is my P1 lying? At the imaginary axis itself, but above the imaginary, above the x-axis. So it will be plus 90. With respect to this, let's say I want to measure for this one. Now for this 0, where is this P2 lying? P2 is lying in the, what is this quadrant? This is the 4th quadrant, right? So this will be something negative, right? This will be something negative. and with respect to this P1, where is this P2 lying? Again in the fourth quadrant. Again this will be negative. So both of them will be in the negative direction and added, right? So yeah, like this you can understand, right? So I am giving you like basic understanding how to calculate the angles. Obviously we'll solve multiple examples there, you will get a better understanding, right? So yeah, just deriving it for now, so not going to waste time because this video has already gone long. So this is my theta P2. So what is my theta departure, right? What is my theta departure? Theta departure of P1 should be equals to 180 plus 14 and minus 19, right? So this is what I get, and this will be almost equals to 104 degrees. Okay, so my theta departure P1 will be almost equals to 104 degrees. Now the pole, what will be the theta departure of P2? Theta departure of P2, it will simply be the complex conjugate. I mean, it will simply be the negative of this one, right? Minus 104. Now what does this represent? So let me paste this here, okay, and reduce the size of this one. So this represents, right, this represents that with respect to my x-axis, my this root locus will start off from 104 degrees, right? So 104 degrees is somewhere around, okay, let me mark this one. 104 degrees will be somewhere around here, right? So my root locus will start off something like this, okay, and minus 104 degrees. Let's calculate the minus 104 degrees. So minus 104 degrees will be, okay, this is, let's say this is 104 degrees, right? 104 degrees, and my minus 104 degrees will be something like this. Okay, so let's say this is minus 104 degrees. So this is where my other branch will start, right? So these two is the meaning of this one. So from where my branches will start, from what angle? So finally I found the unknown, from what angle my other branches will start. Now what is the step 6? It's the boring steps only, right? So we have to find the crossover point, and here, right, we have a valid crossover point because as I'm observing, right, these branches will cross my from right hand side to the left hand side. So this time I will get a valid location of my crossover points. So step 6, cross over points. Okay, so my step 6 is crossover points. So it is simply equals to 1 plus k into s plus, like just put that in the characteristic equation and you will get it. What is my characteristic equation? It is s square minus 2s plus 2, right? S square minus 2s plus 2 equals 0. So this becomes s square minus 2s plus 2 plus ks plus 3k equals 0. So this is s square plus s k minus 2, then plus 2 plus 3k equals 0, right? So now, like what you can do is simply make this one 0 and you will get your crossover point, right? You can do that, or replace s equals to j omega. If you replace this one with k equals to 2, what do you get? You get s square equals to like 8 and s square will be 2 root 2. Okay, or let's replace this with j omega itself. So this one is j omega whole square plus j omega k minus 2 plus 2 plus 3k. Okay, now what does this become? This becomes minus omega square plus j omega k minus 2 plus 2 plus 3k equals to 0 itself. So like now equating the real and imaginary parts. So real part g of h of s equals to 0. So what is this? So this is simply, right, this is simply equals to so like equating the real parts is okay. I can't equate the real parts first because I have to equate the imaginary part first. From there I will get the value of k, right? Sorry, here and copy this one. Okay, the imaginary parts. One thing I know that my omega can't be 0. Okay, why? Because I will have complex conjugate poles. Okay, hence my omega equals 0 is not a solution. Okay, even if you put omega equals 0, you will get that my k becomes negative. Okay, so from there also you can understand, or you can understand I will have imaginary roots on the j omega axis and they will be conjugate to each other, conjugate imaginary roots, right? So hence it can't be equals to 0 because I can only have 2 roots at a time. Okay, so 0, if I take one 0 root, where will the other root lie? Okay, that is the issue. So yeah, I hope you understand that. So omega is not equals to 0. So what I can write, j omega, or not j, sorry, omega into k minus 2 equals to 0. So my k will be equals to 2. So from here I got the value of k and put this value here, right? So we'll write minus omega square plus 2 plus 3k equals to 0. So this is what my so what is my like k is 2, right? So omega square equals to 8. So omega equals to plus minus 2 root 2 plus minus 2 root 2, right? So omega equals to plus minus 2 root 2. So this is what my omega is. So what is my s equals to? S equals to plus minus j 2 root, right? So s is equals to this one. So like this is the value of my location of my roots. So you can solve this using the route also, but no need to because this is the second order only. So yeah, this is the basically like the root locus diagram, right, for this OLTF, right? So I've already drawn it down and written all the values. Like okay, what is the value of k here? K is 2, right? K is 2, value of k is 2. Okay, so this is k crossover, you can write, and these are my crossover points basically, and this is where it starts. And what is the angle? So I can write this angle, right, with respect to my x-axis. Okay, these angles are, right, these angles are, this one was okay minus 104, right, minus 104 degrees, and this one was plus 104, right, plus 104. Okay, so yeah, this is basically the thing. And here, right, I have a break in point and the value of k at that break in point is 16, right, 16.24. okay, and they are terminating. I have a virtual point. So like you can draw this very fast also, but obviously just we are learning right now, that's why I'm drawing it slow. In the next lecture we'll draw it very fast. And here, right, so I have like divided into sections. Where is my system stable, where is my system unstable, that you can see, right? I won't explain it because time is gone. So yeah, just read it for yourself and you will understand. Like in this region, right, my system is unstable, but what is the damping here? It is negative zeta underdamped, right? So hence here zeta is negative and it is underdamped because I have complex conjugate poles. That's why negative zeta underdamped and it is unstable. After that, as it is here, it is marginally stable, right? Marginally stable. I have two poles which is undamped and which are imaginary conjugate, so marginally stable. Then system always lies on here, right? The poles always lie on the left hand side of my S plane, so it is always stable. So it will be always stable. Okay, as the k value is increasing, it will be always stable here, but the damping will be different. Here, right, I have complex conjugate poles. So until here, right, I will have underdamped system. At this point, I will have repeated poles because for the same point at same value of k, I am getting two poles here. After that, they diverge, right? So then they become overdamped. So that is basically underdamped, critical damped, overdamped. So by the variation of k, we can understand the behavior of my system. So I am going a bit fast because time is less. So here, right, this is our root locus. These are root locus. So like this is the MATLAB plot. So from here, right, you can, this is more accurate actually. You can understand this is exactly equals to 104 degrees, right? 104 and minus 104. Okay, so this is just to give you like the proof, right? From MATLAB we are getting the same root locus as we drawn it in the handwritten format. So on the MATLAB also we're getting the same root locus, so our calculations are correct only. Okay, so yeah, just check the values of k and all those things. So it may happen that just some minor calculation mistake may happen, so you can always text me in Telegram. Okay, so yeah, I think that's it for this lecture. If you would like this lecture, then like do hit the like button, and like thank you for watching. And in the next lecture we'll solve more questions and examples, and there your more doubts will get cleared automatically. Thank you for watching.